Good evening, everybody. Am I audible?
Yes, sir.
Okay. So let us start our class now. But again, I find that recording provision is not available here. So some of you must, or one of you at least, must take the screen recording. Can anybody do it? In the last class, someone did it. Can anybody do that? Okay, so please do it and share among your friends. And I'd like to have a copy. So the recording of today's class you send to me also. Everybody's recording, I mean, every day's recording is not needed. I just want to see, it's my curiosity, how it is recorded. I mean, how good is the recording of this method, that I want to see. So please send me a copy of today's recording. Okay then. So today we are going to start our next chapter, that is the chapter on overvoltage in power system and traveling waves. So this chapter we shall discuss today. And after we finish this overvoltage, uh, earth faults, etc., then we shall uh, take up the chapter on cables. The cable, that chapter will be discussed less because most of the things which is covered in this syllabus you have already studied in your power system classes on cables. So only a few topics selectively will be discussed from the topic of cables. I mean, selectively some points will be discussed, and rest of the chapters will be discussed in detail. You tell me whether did I send you the note of chapter 1? I think yes. What about chapter 2? Did I send it? Okay. So let us start our discussions on overvoltage in power systems. Now, actually, there can be three different types of overvoltages that may occur in a power system. Now, these three are power frequency overvoltages, lightning overvoltages, and switching overvoltages. Now, again, power frequency overvoltages, they arise or they crop up in the system mostly due to unbalanced faults or capacity loading like Ferranti effect, etc., etc. Uh, I think you have already studied Ferranti effect. Can anybody say what is Ferranti effect?
So receiving end
Yes, sir.
voltage is
What is
greater
that?
than receiving end voltage is greater than the sending end voltage.
Yes, but how and why
In
it
the low load
happens?
condition or in the lightly loaded condition, due to the presence of shunt capacitance, the receiving end voltage will be greater than the sending end voltage.
Okay, so that is Ferranti effect. But whatever may be the reason, it has been observed that the power frequency over voltage is limited to 20 to 30% of the rated voltage. On the contrary, when we talk about lightning over voltage, first of all, lightning, this is a natural phenomena. This has nothing to do with uh, your system. That is, it is not due to any fault developed in your system or something like that, mal-operation of the system. It is not like that. It's a natural phenomena. But it is lightning is the main consideration for selecting the insulations of any substation or transmission line equipments up to a voltage level of 300 kV. Beyond 300 kV, it is the switching over voltage uh, which is given the most importance, or in other words, we can say that up to a certain voltage starting from 300 kV, both lightning and switching over voltages are taken care of. And in the ultra high voltage level, it is the switching over voltage which actually is considered to determine the insulation level of the system equipments. Now, the reason being, for each and every lightning voltage level, what should be the basic impulse level, impulse withstand level, etc., that is specified in IS specification. It has been found that the overvoltage that results in a system lying within 300 kV operating voltage level, any switching over voltage developed in such systems, the peak value of that over voltage is less than the lightning over voltage that may develop in that system. Therefore, if you select the insulation level on the basis of higher voltage level, then you don't have to be bothered about any over voltage which is magnitude of which is lower than the selected insulation over voltage level. But it has been found that beyond certain value of over voltage, it is the if the switching over voltage is concerned, or switching over voltages, the peak value of those over voltages is higher than the lightning over voltage. In those cases, that is in the high voltage range, you have to consider the higher over voltage, that is the switching over voltage, and you have to select the insulation voltage level accordingly. Now, first of all, let us consider the phenomenon of lighting in brief. Now, I tell you one thing, the exact mechanism behind the lighting is, again, cannot be certainly uh, said, or cannot be certainly explained, but there are different theories which are used to explain the phenomenon of lightning. And we shall discuss one of the theory which is in majority of the cases is used to explain the phenomenon of lightning. Now, lightning, what is lightning? If that point is to be, or if that has to be explained, we can in a simplified manner, we can state it like this: lightning is the discharge between heavily charged cloud and earth. That is the simplest way of defining what is lightning discharge. Now, again, the lightning discharge or process of lightning can be explained, or can be divided into two categories. One is charge formation and the other is discharge. Now, what is said is this: normally clouds have negative charge concentration in the lower part and the positive charge over the upper surface. Now, how these charges develop within the cloud, that is explained in the next sentence. That is, these charges are formed mainly due to air friction and ion conduction. So this is how the charges are found to be, or charges are formed within the cloud. And the distribution of charges is like this: there is negative charge concentration on the lower part of the cloud, and on the upper part of the cloud there is positive charge concentration. Concentration of charges in the lower part of the cloud produces high stress and starts ionization just below the cloud. This point is to be noted carefully. That is, Whenever there is concentration of charge in around any point or any object, electric field strength or the stress around that point or that object will be very high. And since here in the cloud, I'm sorry, in the lower part of the cloud, there is concentration of negative charges. Therefore, what will happen? Electric field strength will be higher there, and if that electric field strength exceeds the ionization strength or breakdown strength of air, then ionization of air just below the cloud will start. This ionization leads to the development of conductive channel. It should be conducting. Now, what really happens is this: just below the cloud, since air has ionized, therefore the air no longer acts as an insulating medium, but on the contrary, a part of air becomes conducting in nature due to formation of both positive ions and electrons. That is why, up to a certain distance, we can think of the or explain the situation like this, as if some conducting channels have developed below the cloud. Now, these negative charges in the cloud comes down through these conducting channels, and the positive charges are absorbed in the cloud. Now, these positive charges means the positive charges which have been formed due to ionization of air, not the positive charges already present in the air. Then what happens? First, ionization takes place, then a conducting channel develops. Through these conducting channels, the negative charges from the cloud comes down to some distance, and the positive charges formed due to ionization of air below the cloud, they flow toward the I mean flow toward the cloud and absorbed in the cloud. Now, this leads to high field concentration at the tip of the conducting channel, and ionization proceeds further. Yes, due to concentration of large number of negative channels coming down from the lower part of the cloud through the conducting channels up to the head or tip of the conducting channel, concentration of negative charges at the tip or head of the I mean conducting channels will be more. And what will happen? Since the charge concentration is more, electric field strength or stress will be more there, and further ionization will start from those points around the tip of the conducting channel. Now, these leading channels are called leaders. That is, the channels through which negative charges come down are called leaders. As these leaders descend in steps, they are also called stepped leaders. When the leaders have reached 50 to 100 meters from Earth, the point of lightning heat is decided, known as the striking distance. Do you understand up to this? Up to striking distance? Do you understand, or do you have any question?
Sir, could you please repeat the striking distance once again?
Yes, striking distance means actually the negative charges from the lower part of the cloud starts coming down through the conducting channels, that is through the leaders. And when there, I mean, the distance between these negative charges concentrated at the tip of the leader and any earth object is distance between the tip of the negative, I mean, tip of the conducting channel or the leader and any of the earth object is within 50 to 100 meter, then which particular earth object is to be hit by the lightning, that is decided. And this distance, 50 to 100 meters from earth, is called the striking distance.
Yes, sir.
Okay. Next is now once the lightning hits any one of the earth object, then what happens? The negative, I mean, the charge cloud through the conducting channel is connected to the ground through the earth object which has been hit by lightning. Therefore, there is a complete short circuit between the upper atmosphere and ground through the conducting channels. And what really happens from ground, positive charge starts flowing flowing through the conducting channel through the conducting channel to the clouds and gradually neutralizes the cloud charges known as return stroke. That is, the charges or the negative charges from the lower part of the cloud comes down through the conducting channels, then at a distance 50, lying within 50 to 100 meters, the earth object to be hit is decided. And when any of one of the earth object is hit by the lightning, these charges flow to the ground through the conducting channel formed between the lower part of the cloud and the earth object. So there is a complete short circuit between the earth and upper atmosphere. And from earth, then positive charges starts flowing through the same conducting channel to the cloud and starts neutralizing the negative charges there. That is why lightning does not continue for an indefinite period. After the lightning hits any one of the earth object, positive charges from earth starts flowing through the same conducting channel and neutralizes the negative charges in the upper atmosphere or in the cloud, and thereby prevents the lightning to continue. Now, the flow of positive charges through the same conducting channel from earth to cloud is called return stroke. Now, lightning strikes are designated by means of kiloampere rating, that is 10 kiloampere lightning stroke or strike, 20 kiloampere lightning strike, like this. Transmission lightning on transmission line. Transmission line contains distributed capacitances and inductances. That we all know. When the lightning hits a transmission line, the lightning voltage moves gradually in both directions by charging the capacitances through series inductances. This is what happens. 90% of the lightning stroke is of negative polarity. Now, another point is this, though that is not shown on in the slide, that is, since the charge particle or negative charges from the lower part of the cloud starts flowing towards ground or comes down through the conducting channels in steps. That is why the leaders are sometimes called stepped leaders. They do not follow any straight path. On the contrary, the leaders are like this. I am enlarging the diagram. The leaders are like this. Can you see this diagram now?
Yes, sir.
Therefore, you see the negative charges do not come down to or following any straight path. On the contrary, they follow the path of such as path of stepped leaders as shown in the diagram. Or in other words, we can say that the lightning strike always follows a tortuous path, not any straight path. That is why whenever there is lightning, you'll see that that is taking place in the upper atmosphere along the tortuous paths, not through any straight path. Now, types of lightning strokes. There can be two types of lightning strokes. One is direct lightning stroke, and the other is indirect lightning strokes. Direct lightning strokes are what? Direct lightning strokes is when the lightning strikes a line conductor directly, or the leader stroke includes positive charges on the ground surface, earth conductor, and other grounded objects. The leader stroke induces. We have just now discussed, or we have just now seen that 90% of the lightning strikes are of negative polarity, or in the last point, 90% of the lightning stroke is of negative polarity. Now, also, in the lower part of the cloud, there is concentration of negative charges. Therefore, these negative charges will induce positive charges on the transmission line conductors or and also in other conductors and grounded objects. Do you agree this point? Agree with this point? That leader stroke induces positive charges on the ground surface, earth conductor, and other
Yes, sir.
grounded objects. Okay. And when lightning strikes a line conductor directly or any object directly, then it is called a direct lightning stroke. On the contrary, indirect lightning stroke is explained like this: a lightning discharge in the vicinity of the line. Say the lightning discharge does not hit directly the line conductor, but the discharge takes place in the vicinity of the line conductor. Then what happens? The field collapses and the induced positive charges on the conductors are released and they start flowing over the line conductors. And you have seen the magnitude of the lightning strike is of the order of kiloamperes. So the positive charges will initiate a current in the transmission line conductors which is of the order of kiloamperes. And these currents, which arises from the fact that the bound charges have become free after there is a lightning discharge. The charges will flow in both the directions, and as a result, what will happen, depending upon the surge impedance of the line and or impedance of other objects, a high voltage will be induced or high voltage will develop across those objects. Therefore, suddenly, suddenly, after the discharge in the vicinity of the line, the insulators and other equipments connected to the lines and earth, they are subjected to over voltage, though they have not been directly hit by lightning, but they are subjected to over voltage because of the I mean because of the lightning because of the occurrence of lightning in the vicinity of the line. That is the induced lightning, indirect lightning strokes. The induced positive charges on earth were travel down to earth through the towers, and those on the phase conductors travel along the conductors and are dissipated through corona and resistance loss. That is there. So do you understand what is direct lightning stroke and what is indirect lightning stroke? Tell me.
Yes, sir.
Okay. Now, velocity of propagation of traveling wave. These, I think you have already studied, na?
Yes,
Have you
sir.
studied? Huh?
Yes, sir. In power system.
In power system. So just quickly go through the slides since you have already studied. I don't want to spend much time on it. Did you study it in this way, or the approach was something different?
Sir, is this the analysis of long transmission line? Then we studied that.
No. How did you find out the velocity of propagation, surge impedance, etc., considering a long distance transmission line like
Yes,
this?
sir. Yes, sir.
Okay. So this is not a new thing. So just recapitulate it quickly, going through the slides, and when you finish going through the slide, you just tell me so that I can show you the next slide.
Sir, this slide is complete.
Okay, so now this one. Is it okay?
Yes, sir.
Okay, then.
Okay, sir.
Okay, then.
Yes, sir. Okay, sir. Completed. Sir, finished.
Okay. Next is lightning hits the line. Suppose here we consider that a lightning of strike of I kiloamperes hits the line conductor like this, and half the total current flows through the two adjacent towers, because lightning hitting the conductor, line conductor, divides itself into two parts. So I by 2 will flow in either direction. We assume that I is equal to 10 kiloampere. Then E, the EMF that will be induced, or the voltage drop that will take place due to the flow of current on through the line conductors, will be equal to surge impedance of the line, let it be 500 ohm, into 10 by 2, that is 2.5 megavolts. This voltage will travel toward the tower and will appear across the line insulators and may lead to flashover. Do you understand this? What happens when the lightning hits the line conductor directly? What is the magnitude of voltage drop or traveling voltage along the transmission line which appears across the insulators and other equipments connected to the system? Huge over voltage, 2.5 million volt. If you consider, or if you find out the insulation level for even, I mean, 11 kV, it is 75 kV. For 33 kV, it is 166 kV, or like this, I am telling you. So 2.5 million volt is not any insulation level for most of the transmission lines. I should not say any transmission line, most of the transmission lines, this is not the acceptable or usable insulation level. Therefore, all of them will be subjected to overvoltage. Traveling wave, whenever meets a discontinuity, that is a change in surge impedance. This is another thing, reflection and refraction of waves. Have you studied this already? Reflection and refraction of traveling waves?
No, sir.
You have not studied. Okay. Traveling wave, whenever meets a discontinuity, that is a change in surge impedance of the line, gives rise to two waves, one of which is transmitted forward and the other is reflected back. This discontinuity in the line may rise at the junction of two overhead line and a cable, the end of a line, forked line, the junction of a line with terminal apparatus, etc. That is, whenever a traveling wave finds or meets a discontinuity, that is, there is a change in the surge impedance from the path where it has been initiated and the path where it has to flow next, there will be a reflection and refraction. Now let us discuss those things. Now here we consider there are two lines, one having surge impedance Z1 and the other is having surge impedance Z2. And we further assume that Z2 is greater than Z1. Then Vt, the transmitted voltage, is equal to Vt is equal to Z2 into It. We further assume that II is the incident, Vi is the incident voltage wave, II is the incident current wave, Vr is the reflected voltage from the junction, IR is the reflected current, VT is the transmitted voltage, and IT is the transmitted current. Uh, Here, we should have included one more point. I mean, anyway, let me insert a blank side here. Okay. Now, for the time being, you just assume when I send you the note, I shall send you after corrections. We further we assume, I repeat, V suffix I is the incident voltage wave as it is shown over here. I suffix I is the incident current wave. V suffix R is the reflected voltage wave reflected from the junction of discontinuity. IR is the reflected current wave, and IT is the transmitted current wave, VT is the transmitted voltage wave. Now, if Z2 is the surge impedance of the second line and IT is the current flowing through them, then obviously VT can be written as equal to Z2 into IT, from where we can write IT is equal to VT by Z2. Let that be our equation 1. Similarly, VR is the reflected voltage wave and current flowing through the line 1, the reflected current flowing through the line 1 is IR. Then IR into Z1 will be equal to VR. IR into Z1 is equal to VR, from where we can write IR is equal to VR by Z1. And obviously, if VI is the incident voltage, II is the incident current, then II into Z1 will be your VI, from where we can write II is equal to VI by Z1. Do you understand these equations? Very simple. Any question regarding these equations? Any questions?
No, sir.
Okay. Now, as Z2 is greater than Z1, we can see that VT, transmitted voltage, greater than both VR or VI. Since the voltage and current waves are continuous at the junction, it may be written that VT is equal to VI plus VR. Do you understand this equation or not? You tell me.
Sir, the equation 4 I cannot understand.
Now, here what happens? This is the incident voltage. At the junction, what will happen? A part of the voltage will be transmitted forward, and part will be reflected back. Now, what will be the net voltage at the junction?
Okay, sir.
VI plus VR.
Yes,
That
yes,
is VT.
yes,
That
yes.
is written here. Equation 4. And since IR is the flowing in opposite direction to that of II, then if II is considered positive, then IR is considered negative. Therefore, IT should be equal to II plus of minus of IR. That let that be equation 5. According to Kirchhoff's current law, we can write this.
Yes, sir.
Okay, fine. Then these equations, these derivations are very simple. VT is equal to VT by IT is equal to Z2 from our equation 1. VT by IT is equal to Z2. So VT by IT is equal to Z2, and VT can be replaced by VI plus VR, and IT can be replaced by II minus IR. Do you agree?
Yes, sir.
And II is equal to VI by Z1.
Yes, sir.
IR is equal to VR by Z1.
Yes, sir.
Then we can write Z2 by Z1 is equal to VI plus VR by VI minus VR.
Yes, sir.
Now let this be our equation 6. Now this using componendo and dividendo, what we can write? Can we write this equation 7? VR is equal to this Z2 minus Z1 by Z2 plus Z1 into VI. Can we write this? Equation 7?
Yes, sir.
Okay. From equation 5, IT is equal to II minus IR, because II minus IR that we have seen from equation 5. This one. Okay. So from here, IT is equal to II minus IR. Now for IT, if we substitute VT by Z2, II is equal to VI minus Z1, and this is VR by Z1, then what we can write? VI minus VR is equal to VT into Z1 by Z2. Let that be equation 8. Do you understand this? Equation 8. Do you understand?
Yes, sir.
Then from adding 4 and 8, this is 8, this one is 8, and 4 is this one. Vt is equal to Vi plus Vr, and 8 is this one. Vi minus Vr is equal to Vt by Z1 by Z2, Vt into Z1 by Z2. So if we add them together, 2 Vi gives you this. From where we can write Vt is equal to 2 into Z2 by Z1 plus Z2 into Vi. Let that be our equation 9. So we have been able to express all that VR, Vt, etc. in terms of Vi and also the surge impedances. Is it clear? Up to equation 9.
Yes, sir.
Now we have to consider a few special cases. Thereafter, we shall take 5 minutes break. First, case 1, we consider, just a minute. Z2 is equal to infinity, that is open circuited line. In that case, what will happen? IT is equal to 0, Vt by Z2, that is equal to 0. Okay. This means no current is transmitted. And VR is equal to, we have just now deduced the expression for VR, that is Z2 minus Z1 by Z2 plus Z1 into Vi. Since Z2 is equal to infinity, then what we can write? Z2 minus Z1 by Z2 plus Z1 will be almost same. Therefore, VR can be written as almost equal to Vi. Equation 2, do you understand this? If Z2 is infinity, then compared to
Yes, sir.
Z2, Z1 can be neglected.
Yes, sir. Understood.
Therefore, Vt can be written as equal to Vr plus Vi, that is equal to 2 Vi.
Yes, sir.
Therefore, It is equal to Ii minus Ir, that is equal to 0, and Vt is equal to 2 Vi. Therefore, when a traveling wave meets an open circuit, we see that the transmitted current becomes 0 and the voltage becomes double. We are already used to this effect known as, tell me, at the beginning of the class, I asked you about Ferranti effect. What happens in Ferranti effect? Receiving end voltage becomes double the sending end voltage.
Yes, sir.
That is because of loading of long unloaded line.
Yes,
And
sir.
when the line is unloaded, current is equal to 0. So that part is verified. Here, in the case of open circuited line, we see that the current is 0, but the voltage is double. So that is our first case. Next is short circuited line, case 2. Z2 is equal to 0. Then VR will be equal to what? VR will be equal to minus of Vi. VR is expressed like this, Z2 minus Z1 by Z2 plus Z1 into Vi. Now, if Z2 is 0, then it becomes equals to minus Vi. VR is equal to minus of Vi. And IR is equal to VR by Z1. As VR is equal to minus Vi, then IR will be equal to minus I1, not I1, I suffix I or II, as it is seen, or as it is seen from equation 2. Therefore, Vt is equal to 0, Vi plus VR, as VR is equal to minus Vi, and It will be equal to 2I to II. Is it okay?
Yes, sir.
So, in a short circuited line or short circuited system, what happens at the point of short circuit? The voltage becomes 0, but the current becomes much more. Here we see that it becomes double. Is it clear?
Yes, sir. Yes, sir.
Resistance termination. Here, what all we have to do? We have to replace Z2 by R. You see, Vt is equal to Vi plus Vr. Vt is equal to It into R. Since here it is Z2 is replaced by R, so Vt can be written as equal to It into R. And finally, we get like this. This is 1, this is 2. Finally, we get Vt is equal to 2 into R by R plus Z1 into V1. That is equation 3. So, general expression for Vt is 2 into Z2 by Z2 plus Z1 into Vi. Here Z2 is replaced by R. So the final expression becomes 2 into R by R plus Z1 into Vi. Clear? Is it clear now?
Yes, sir.
And Vr is equal to Vt minus Vi. Vi plus Vr is equal to Vt. So we can write Vr is equal to Vt minus Vi. That is, and expression for Vr is Vi into Z2 minus Z1 by Z2 plus Z1. So that becomes equals to R minus Z1 by R plus Z1. I hope you understand this. the expression for VR. Can we move to the next slide?
Yes, sir.
Uh, Case 4, line terminated with surge impedance. That is, if a line is terminated at its own surge impedance value, that is the Z2 is equal to Z1. In that case, VR Z2 minus Z1 by Z2 plus Z1 into Vi is equal to 0. Therefore, that is, there will be no reflection of voltages from the uh, line termination, because here, since the surge impedance of both the lines are same, so there is no discontinuity. Same line is there. So when any line is terminated at its surge impedance, there is no reflection from that point. And IR, since VR is equal to 0, IR is also equals to 0. And VT is equal to VI plus VR, that is equal to VI, since VR is equal to 0. That is, the entire amount of incident voltage is transmitted forward. And IT is equal to II minus IR, since IR is equal to 0. Therefore, the entire amount of incident current also is transmitted forward. So there will be no reflection. And this feature is very well used in different laboratories and in other parts. In our laboratory also, quite often we have to conduct transformer testing, etc. And for doing so, what all we have to do, we have to actually record the voltage and current waveforms applied across the transformer and resulting voltage wave or the impulse voltage applied across the transformer winding and the resulting current. The waveform of both of these two have to be recorded, and that recording is done on the computer screen. And you see, therefore, from the transformer and also from the impulse generator end, two signals are to be taken to the input of the uh, computer. And obviously, the input impedance of the computer and that of the impulse generator or transformer, they do not match. So perfect matching of the impedances are done so that no reflection takes place, so that the voltage at the computer terminal becomes high. That is done. And by perfect matching of the cables, actually we record the voltage and current waveforms on the, in computer. So now we shall take 5-6 minutes break, then we shall again resume. Can you resume now?
Yes, sir.
Now let us consider the case of junction of a transmission line and a cable. Consider a lightning impulse developing in an overhead transmission line meets a cable. Line of surge impedance of the line, let us consider as 500 ohm and that of the cable to be 50 ohm. Now we know this is the expression for transmitted voltage Vt is equal to 2 into Z2 by Z1 plus Z2 into Vi, and Z1 is equal to Z line, Z2 is equal to Z cable. We have assumed that the voltage, lightning impulse is developing in the line and ultimately enters the cable. Therefore, the transmitted voltage will be 18.2% of incident voltage. Therefore, it is seen that the cable reduces the surge voltage by 18.2% if it is connected to a transmission line. That is our observation. I hope you have understood this. Is there any question regarding this? Yes, any question? Any question up to this? Somebody should tell me whether you have understood this or not. Yes? Okay. Therefore, what will happen in the reverse case? Suppose the lightning wave impulse is actually initiated in the cable and it enters the transmission line. Then same relationship will be valid. Vt will be equal to Z2 by Z1 plus Z2 into Vi. Only thing is this time Z2 will be more, that is 500 ohm, and Z1 will be less, that is 50 ohm. Therefore, the case is this one. Vt becomes 1.82 Vi. That is, the transmission voltage will be 82% higher than the induced voltage. Do you understand this point or not? You tell me.
Yes, sir.
Okay. Now, this feature is very effectively used for interconnecting two transmission lines. What happens? Two overhead lines joined by a cable. What happens? You see, these are the two lines, and we assume that that here in transmission line one, the impulse voltage is incident, that is Vi, and that voltage travels towards the interconnection or discontinuity or junction between the transmission line and the cable, and a part of the voltage enters the cable. Now, this voltage entering the cable again uh, travels forward and finally reaches the second junction where it again finds another discontinuity, and obviously a part of the voltage is transmitted forward. Therefore, here Vt1 transmitted voltage, as we have seen, when the voltage is incident on the transmission line and enters the cable, the transmitted voltage is 0.182 Vi. So this VT1 will be 0.182 VI, and that voltage when reaches the second discontinuity and transmit a part of which is transmitted in the transmission line, that is VT2, that VT2 will be equal to 0.182 into 1.82 VI. Multiplying these two, we get finally VT2 becomes 0.3312 VI. That is one third of VI. Therefore, if we interconnect a two transmission lines with the help of a cable, then that traveling wave in the second line becomes one third that of the traveling wave in the line 1. Therefore, the cable is therefore useful in reducing surge transmitted to substation. So that feature is very well or often used in substations. Any question regarding this?
No, sir, no question.
Okay. Next, let us consider fork lines. Now here we consider there is an incident line to which two outgoing lines are connected. These two lines are parallel. They are in parallel. And we assume that incident voltages are VI and VR. Here it has been written as EI. And though in the diagram it has been shown as VI, but here it has been written as EI, ER, ET, etc. So just please accommodate. Uh, Here we assume that EI and II be the incident voltage and current. Similarly, ER and IR be the reflected voltage and current. ET and ET and IT2 be the transmitted voltage and current along Z2, and ET and IT3 be the transmitted voltage and current along Z3. So these are our assumptions. Now IT2 will be obviously ET divided by Z2, and IT3 will be equal to ET by Z3. Do you understand this? Same
Sir, why
voltage.
transmitted voltage is same for these two lines?
They are in parallel. These two lines are in parallel. That is
Oh,
why the
okay, sir.
voltages will be same.
Okay, sir.
Okay. Therefore, we also know IT is equal to II minus IR. And here IT is nothing but sum of the two transmitted currents, IT1 plus IT2. And II can be written as equal to EI by Z1 minus ER by Z1. That is equal to ET by Z2 plus ET by Z3. Or EI by Z1 is minus ET minus EI by Z1. Now ER can be written as equal to ET minus E1, because we know transmitted voltage is equal to reflected voltage plus incident voltage. Therefore, reflected voltage can be written as equal to ET minus E1 or EI, sorry, not E1. Agreed? ER is equal to ET minus EI. Agreed? Do you understand this point, this step or not?
Yes, sir.
Okay. From therefore, after simplification, we can write ET is equal to this one. 2E1 by Z1 by 1 by Z1 plus 1 by Z2 plus 1 by Z3. This is the expression. Now, if instead of two lines, we consider n number of lines are connected here. Therefore, IT should be replaced by IT1 plus IT2 plus IT3 up to ITN. Let that be equation 1. Again, IT is equal to II minus IR as before. And VT is equal to VI plus VR. That should be equal to IT into Z equivalent if we consider that the equivalent impedance of all these lines connected in parallel is Z equivalent. Therefore, IT can be written as equal to, I mean, VT can be written as equal to IT. Let IT be the current flowing through that equivalent line, that IT into Z equivalent. And from 1 we get VT by Z equivalent. IT can be written as equal to VT by Z equivalent. That should be equal to VT by Z1 plus VT by Z2 plus VT by Z3, etc. Let this be our equation 5. Is it clear up to equation 5?
Yes, sir. Clear.
From 3, sorry, 3 is this one. From 3, what we can write? VT is equal to 2 VI by Z1 plus Z equivalent into Z equivalent. Can we write this from 3? VT is equal to 2 VI by Z1 plus Z equivalent into Z equivalent. Can we write this? This is 3. Can we write this from equation 3? Okay. Up to this, it was okay, na?
Yes, sir.
Now this, can we write 1 by Z equivalent is equal to this?
Yes, sir.
Again from 2, IT is equal to II minus IR. And IT is equal to this. II can be replaced by VI by Z1 and IR can be replaced by VR by Z1. Therefore, we can write VI minus VR is equal to IT into Z1. Now 3 plus 7. 3 is this one. VI plus VR is equal to IT into Z equivalent. And 7 is this one. VI minus VR is equal to IT into Z1. So if we add them together, we get 2 VI is equal to IT into Z1 plus Z equivalent. From where we can write this? IT is equal to 2 VI by Z1 plus Z equivalent. Can we write this up to equation 8? Is it okay? Please tell me.
Yes, sir.
Okay, now you tell me from 3, VT is equal to this. Can we write 2 by V1, 2V1 by Z1 plus Z equivalent into Z equivalent? From 8, we know IT. From 3, what we can write from 3? VT is equal to IT by Z equivalent, IT into Z equivalent. And from 8 we can write IT is equal to 2 VI by Z1 plus Z equivalent. That into Z equivalent will be your VT. What we are writing, VT is equal to IT into Z equivalent. And from 8 we know IT is equal to 2 VI by Z1 plus Z equivalent. So VT can be finally written as equal to 2 VI by Z1 plus Z equivalent into Z equivalent. This one is your IT from equation 8. So IT
Yes,
into
sir.
Z equivalent. So this is our equation 9, where n lines are connected to the bus having same surge impedance, same surge impedances Z1, then Z equivalent will be equal to Z1 by n. Therefore, Vt will be equal to 2 into V1 plus Z1 by n into Z1 by n. That is equal to 2 Vi plus n by 1. Is that okay? Do you understand this or not?
Yes, sir, understood.
Understood. The above equation shows that the transmitted, the voltage transmitted through diverged lines of the busbar is reduced to 2 by n minus 1 times the actual voltage. Okay, okay. Reduced to the ratio 2 by n minus 1, where n is the total number of lines through which the wave is transmitted. Is that point clear?
Yes, sir.
Okay. Next is groundware. Importance of groundware. Now, in high voltage transmission system, apart from the line conductors or live conductors or transmission line conductors, at the top of the transmission tower, another conductor is allowed to run, and that conductor is that conductor is maintained at ground potential, and that conductor is normally referred to as groundware or earthware. Now, this wire or this conductor acts as a shield to the phase conductors and reduces the probability of direct lightning strokes. Now, these ground wires or ground conductors, they must meet the certain conditions or certain criterion they should fulfill. Only then proper protection can be provided by the ground wire to the phase conductors or phase wires. The first point is this: the ground wires must be kept high above the line conductors and disposed in such a way as to interpret the direct stroke. It is customary to call the space around a ground wire in which the probability of lightning stroke is low as the protective zone. The protective zone of a ground wire is the region below a quarter circle, drawn with its center at the height of the ground wire and its radius equal to the height of the ground wire above the ground. The phase conductors needs to be located in protective zone. Do you understand what does really protective zone means? If you don't understand, you tell me, I'll explain.
Sir, please repeat once again.
Now, the protective zone is defined by a quarter circle. It is a region below a quarter circle. To be more specific, the protective zone is described as a region below a quarter circle. Now, this quarter circle is drawn with its center at the height of the groundware, and its radius will be equal to the distance between the groundware and earth. And the phase conductors must be placed within the protective zone. Is that clear now?
Yes, sir.
Okay. Next is, these are the two other requirements. Groundwares must have enough clearance above the line conductors at mid-span to avoid side flashover. Yes, the ground wires are maintained at ground potentials. On the contrary, the live conductors are held at live potential. Now, there should be sufficient clearance between the live conductors, which are at live potentials, and the earth wire or ground wire, so that there is no flashover between the line conductors and ground conductors or ground wires. But you are already accustomed with the term sag that is taking place in the case of transmission lines in the mid-span between the two transmission towers. Are you familiar with the terms sag? So, same thing, there is a chance of occurring sag in the case of ground wires as well. If that happens or if that occurs, then what will happen? The distance between the ground wire and the live conductor will reduce due to sag, formation of sag. And when the distance between the two conductors reduces, there is a chance that the electric field between those 2 points will increase where the distance has reduced, has been, or the distance has become less. It will reduce, I mean, the electric field strength will go up, and if it exceeds the breakdown strength of air, there can be ionization of air or failure of air, resulting in the development of fault in the system. That's why ground wires must have enough clearance above the line conductors at mid spans also to avoid side flashover. Next point is the tower footing resistance must be low enough to avoid flashover. By the term tower footing resistance, we mean that each and every tower at its base develops some resistance. That resistance is normally referred to as tower footing resistance, and the ground wire to provide effective protection against lightning to the phase conductors, the tower footing resistance should be as low as possible. Why it is so, that we shall discuss after some time. Now, let us consider few cases. The first one is lightning hit on the ground wire. Here we assume that again a current, lightning current of magnitude I strikes the ground wire, which after striking the ground wire gets divided into two parts, I by 2 in either, and flows in both the directions. Now, VI, incident voltage, will be equal to I by 2 into surge impedance of the ground wire, ZZ. Again, we assume that the surge impedance of the ground wire is 500 ohm, and that of the tower body is 125 ohm. And here it has been assumed, as shown in the diagram, that the tower footing resistance is 10 ohm. Clear? These are our assumptions, and also we assume that the lightning strike is of 5 kiloampere rating. Therefore, the incident voltage will be equal to 5 into 500 by 2 kV, that is 1250 kV. So this much amount of voltage will start traveling in either direction. Clear? Is it clear?
Yes, sir.
Now what happens? Voltage transmitted through the tower. Now this voltage, 1250 kV magnitude of voltage, when reaches this point, finds discontinuity, one and sorry, it meets two parallel paths having different surge impedances, one along the line having the same surge impedance, and the other through the body of the tower to ground. It is having different surge impedance than that of the line. Therefore, we arrive at a situation like this. Transmitted voltage is, we know, 2 into Z equivalent by ZZ plus Z equivalent into VI. We have seen in the case of fork lines. So what is Z equivalent that has been calculated here? 500 into 125 by 500 plus 125. These two are in parallel. You see, these are the two. One is the transmission line and the other is the tower body. So the equivalent impedance will be 100 ohm. Therefore, the transmitted voltage through the body of the tower will be equal to this one, 416.67 kV. Is it clear to you all?
Yes, sir. Clear.
Now, this voltage instantaneously appears across the line insulators, which may produce back flashover. Suppose we talk or we consider the case of 132 kV line, or say 75 kV line, whatever. So the line conductor is maintained at a potential of 132 kV, or in the case of 75 kV, it will be 75 kV. The insulators or the other equipments provided in the system along with the transmission line are good enough to withstand such voltage applications. But suddenly, if the tower body is subjected to a voltage of 416.67 kV, instead of earth potential at the top end of the insulator, this voltage will appear, and at the bottom end, there may be 75 kV, 11 kV, or some other voltage. Therefore, normally in the case of failure of suspension insulators, we have seen that it fails starting from the bottommost unit where it supports the live conductor. And then the flashover extends in the other direction, and finally the entire unit or the entire string of suspension insulators, across them the flashover occurs and the live potential is transmitted from the line conductor to the earth at the tower crosser. Now here, in the thing is just opposite. At the earth point, the voltage has suddenly increased up to the level of 416.67 kV. At the live end, the voltage is somewhat lower. So there may be a chance that the flashover, instead of taking place from the live end to earth end, there may be flashover from earth end to live end. And that is why it is called a back flashover. But There is a point in real case, the insulators are not subjected to such high voltages because of a negative reflected voltage from the tower base. This phenomena is explained in the next slide. Backflash over, is it clear to you all? Tell me.
Yes, sir.
If the tower footing resistance is 10 ohm, then reflected voltage from the tower base can be computed using the same relation R minus ZT by R plus ZT into VT2. That is equal to 10 minus 125. 125 is the surge impedance of the tower body by 10 plus 125 into 416.67 kV. Therefore, a negative reflected wave of magnitude 355 kV will be will come across the insulators from the tower base. In the time required by the peak value of incident wave to reach the insulator, the reflected wave from the junction of the tower and ground also reaches the insulator. So the resultant voltage appearing across the insulator is 61.67 kV. In the case of 11 kV system also, just at the some time back we were talking about the basic impulse level. For 11 kV system, all the insulators are supposed to withstand 75 kV voltage. So if a voltage of magnitude 61.67 kV appears across them, that voltage they will be able to withstand. Now, so here, had the value of R were even less, say for example 5 ohm, then what would have been the magnitude of this reflected voltage? You just find out yourself. Someone should calculate. Have anybody calculated?
Yes, sir, it is coming.
How much it is coming?
Sir, VR is coming the minus 355.0028.
No. I tell you to calculate the magnitude of surge impedance or tower footing resistance to be 5 ohm instead of 10 ohm, and see what is the magnitude of reflected voltage. In place of 10, you use 5.
Sir, minus 384.586.
Minus 384. Yes. So we see that with reduction in the value of tower footing resistance, the voltage is even reflected voltage is even more, and the net voltage appearing across the insulators is much less. Therefore, with the less, as the voltage, I mean magnitude of the surge impedances decrease, we see that the reflected voltage from the tower base will be more and less voltage will appear across the insulators. That is why the value of the tower footing resistance should be as low as possible so that the ground wires can provide proper protection. Is the point clear to you now?
Yes, sir.
Now, can we continue our class till 9:30? You tell me. Okay. Case 2. Lightning hit the tower. Just a minute. আমি না এখনো অনলাইন ক্লাস নিচ্ছি, আমি আপনাকে একটু পরে ফোন করছি, সারাদিন আজকে ওই গেছে আর কি। হ্যাঁ হ্যাঁ হ্যাঁ, আমি আপনাকে ফোন করে নেবো। আমি মেসেজটা দেখলাম আপনার, হয়েছে, তাহলে হয়েছে তো। হ্যাঁ 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 হ্যাঁ, এই তো মহা মুশকিল, কবে মিটিং হবে। আচ্ছা, ঠিক আছে, ঠিক আছে, ওকে। আচ্ছা আচ্ছা আচ্ছা, থ্যাংক ইউ। Next case. Now here, lightning, in the previous case, in the case 1, we considered the case when we assume that lightning hits the transmission line or ground wire, not transmission line. Here we see that in though the light, I mean earth wire or ground wire is there, but lightning directly hits the tower like this. So when this happens, there are practically three parallel lines. One is through the tower body, and there are two parallel paths via the two outgoing earth wires. So we have a system like this, and the three currents will be equal to I1, I2, and I3, and the net current is, say, I, total current. I1 is the current flowing through one line, I3 is the current flowing through the other line, and I2 is the current through the I2 and I3 are the two currents flowing through the ground wires in either directions. And I1 is the current flowing through the tower body. We again assume that the tower footing resistance to be 10 ohm, ZZ surge impedance offered by the ground wire, that is 500 ohms, and Z equivalent we'll find out. And actually the surge impedance of the tower body is 125 ohm. Now, can you find out or verify whether this is the Z equivalent? Somebody? Can anybody find it out? 1 by Z1 plus 1 by Z2 plus 1 by ZT, whether it is 83.33 or not. Okay, so that is the equivalent surge impedance. Now, again, we assume that the lightning is of 5 kiloampere magnitude. Then the incident voltage will be equal to I into Z equivalent, that is 416.65 kV. However, without the ground wire, if there was no ground wire, then what would have been the incident voltage? 5 into 125, that is 625 kV. That is, the ground wires have reduced the incident voltage developing due to lightning. That fact is verified. Do you understand this or not? Do you understand or not? You tell me. Should I repeat this point once again?
Sir, understood.
Understood. Now again, this voltage Vi will travel towards the tower base and the reflected negative voltage will develop. Let us find out the magnitude of the reflected negative voltage using the same method, same relations, R minus Zt by R plus Zt into Vt, that is equal to minus 355 kV, so that the resultant voltage is approximately 61.67 kV as before. So it can be concluded that the system comprising the tower and ground wires always keeps the resultant voltage to 61.67 kV. Next is Bewley's lattice diagram. Now, this is one concept I just want to introduce. We shall not discuss it in great detail because actually diagram. This is a diagram or pictorial method, I should say, which helps us in finding the magnitude of the traveling wave at any particular instant of time through the transmission line. We have by this time seen that whenever a traveling wave meets a discontinuity, a part of the traveling wave is transmitted forward and a part is reflected back. And if there are a number of discontinuities in the line or in the transmission system, then this reflection and refractions of traveling waves will be a continuous process. So at a particular point or particular node in the transmission system, if we have to find out the magnitude or the status of the uh, traveling waves up to the point under consideration, then this Bewley's lattice diagram provides a method for finding out that. This is a diagram and the method was suggested by a technocrat or technologist or an engineer, we should say, whose name is Bewley, and that is why after his name the method of this this method has been named after his name, Bewley's lattice diagram. Now, as it is mentioned over here in the slide, that surge on a power system are subjected to repeated reflections at terminations, junctions, towers, and similar discontinuities. It is necessary to consider the successive reflection of traveling waves. Bewley suggested a simple time-space diagram or lattice diagram method. The lattice diagram is explained in connection with calculation of voltage buildup at the ends of a short length of an underground cable connected between two overhead transmission lines as shown in the figure below. So this method is basically restricted to the case when two transmission lines are joined together with the help of a cable for reducing the voltage of transmission from line 1 to line 2. And at either end of the line and cable, there will be successive reflections and refractions. And in such cases, this Bewley's lattice diagram could be very well used. Now let us consider this diagram. This is one line, this is cable, and this is the second line. Now we have assumed that the surge impedances of line 1 and line 2 are equal, and that of the cable is different. And here in line 1, there is an incident traveling wave which, when meets first discontinuity, that is junction 1, a part of the wave is transmitted forward in the cable and a part is reflected back in the transmission line 1. Now the voltage wave which is transmitted forward in the line, I mean in the cable, that wave when reaches junction 2, that is the second discontinuity, again a part of the wave is reflected back into the cable and a part is transmitted forward in the transmission line. That way, if we consider the time starting from t is equal to 0, then t is equal to t is equal to t, I mean 2t, then at different instants of time, different magnitude of transmitted voltages will enter the second transmission line or second transmission, I mean transmission line or second transmission conductor. Here we assume that Z1 is the surge impedance of the line, Z2 is the surge impedance of the cable. Alpha 1 is the cable to line reflection factor. Alpha 2 is line to cable reflection factor. The reflection factors can be calculated very well using the relationships which we have already developed. That is VR is equal to Z2 minus Z1 by Z2 plus Z1 into VI. That Z2 minus Z1 by Z2 plus Z1 is here is your alpha. That is the reflection factor. And beta 1 is the line to cable transmission factor. Beta 2 is the cable to line transmission factors. Now these transmission factors are also the same as that we have already derived, that is 2 into Z2 by Z1 plus Z2. Only thing in the case of beta and beta 1 and beta 2, values of Z1 and Z2 will be interchanged since they, I mean, reflection and transmission, I mean, reflection and refraction takes place from different ends. Once it is taking place from the cable end, being reflected, it enters the line itself. But when it happens or takes place in junction 2, at the junction 2, reflection is taking place from the junction 2 and the reflected wave enters the cable, not the transmission line as it is in the case of junction 1. That is why in the case of finding out the reflection factors, only the values of Z1 and Z2 have to be interchanged. Other things, the basic formula will remain same. Now here, let a surge voltage of magnitude V travels along Z1 towards the junction of Z1 and Z2. As the wave reaches junction 1, a fraction of the incident voltage wave is reflected back to the transmission line and another fraction is transmitted into the cable and travels towards the junction of Z2 and Z1. Do you understand these points? And when it reaches another junction Z2, a fraction of it is reflected back into the cable and other fraction is transmitted into the overhead line. Do you understand this point? These we have already discussed.
Yes, sir.
Okay. The voltage reflected back into the cable at the junction of Z2 and Z1 travels into the cable towards the junction 1 of cable and a fraction of this is again reflected into the cable while another fraction is transmitted into the left hand side overhead line. Should I show you the diagram or do you understand this sentence? Here what happens? First, a part is reflected back to the line itself here at junction 1, and another part is transmitted forward, which gets reflected. This transmitted wave also reflected back. A part of the transmitted wave is reflected back into the cable. Another part is transmitted forward into the transmission line. Now, this reflected wave, when again meets junction 1 or reaches junction 1, a part of it will be reflected in the cable itself and a part will be transmitted forward. Likewise, a successive reflection and reflection will continue. Do you understand this point? Do you understand or not? You tell me.
Yes, sir. Understood.
Okay. Now let two vertical lines are drawn at the two ends of the cable. These two vertical lines are made to represent time by choosing proper time scale. That is done. The t is equal to 0 represents the instant when the incident wave reaches the junction of Z1 and Z2, and gamma represents the transmit time for the waves from end to end of the cable. That is, any wave entering the cable will reach at the other end of the cable in time gamma. Now let us OA represent the refracted wave into the cable. AB represents the reflected wave at the junction of Z1 and Z2. BC, CD, D, etc. represent successive reflected waves. Now let me show you the diagram. Let this be the voltage. This is Z1, this is Z2, this is Z1. Again, I am sorry. Now this is the 0 instant. Here T, when reaches this incident traveling wave, reaches node 1 or junction 1, a part will be transmitted forward into the cable, a part will be reflected back. Alpha 1 into V, alpha 1 is our reflection coefficient Z1 minus Z2 by Z1 plus Z2. So that into V will be the first reflected voltage in line 1. And the first transmitted voltage into the cable will be beta 1 into V, and beta 1 is 2 into Z2 by Z1 plus Z2 into V. That will be the first reflected voltage. Do you understand these two, alpha 1 and V, beta 1 and V? Tell me.
Yes, sir.
Okay. Now this beta 1 into V, on reaching junction 2, a part of this beta 1 into V will be transmitted forward into line 1, line 2, and a part will be reflected back into the cable. Now, to find out the reflected voltage wave, what all we have to do? We have to multiply beta 1 into V by the reflection coefficient. But this time the reflection coefficient will not be alpha 1, but it will be alpha 2, because it is taking place from the cable, I mean line end to cable. Here it was line end, from cable end to line. So this is alpha 1, Z1 into Z1 minus Z2 by Z1 plus Z2. But here, what will be Z1? Z1 will be your Z2, and Z2 will be Z1. Do you understand this point or not?
Yes, sir.
So we find out this is alpha 2 into beta 1 into V. And here it will be beta 2 into beta 1 into V. For beta 2, this time, Z2 will be 2 into Z1 by Z1 plus Z2. This time, here it was Z2 was the surge impedance of the cable. But when you find out beta 2, Z2 will be surge impedance of the transmission line. So we find out beta 2 into beta 1 into V. Like this, we can find out the different reflected and transmitted waves in the two lines as well as within the cable. Now, what Bewley suggested is these are the times, what are the different voltages. Now, this point is important. The voltage at any point on the system can be obtained at any instant by algebraic addition of all the waves that have passed the point in both directions up to the instant under consideration. And thus, for the voltage at N2 of the cable, following voltage fluctuation occur, T is the less than 0, voltage is equal to 0, because we have assumed that the time taken for traveling the wave from one end of the cable to the other end of the cable is gamma. So when it is less than gamma, it will not reach the other end of the cable. So at T is equal to less than gamma, the voltage is 0. Now from here, it will be reflected back and come over here. So here it is gamma plus gamma plus gamma, 3 gamma. When the volt at 3 gamma, the voltage will be T tau is less than T less than 3 gamma will be beta 1 into V plus 1 plus alpha 2. Why it is so? Beta 1 is into V is this one, the voltage, and the second voltage that is reflected from here is alpha 2 into beta 1 into V. Now when it is time is equal to 3 tau, then this fraction we have to take, alpha 2 into beta 1 into V. But when it is less than 3 tau, only these two voltages are to be considered. Therefore, the voltage is beta 1 into V into 1 plus alpha 2. You tell me whether you have understood this or not, then we shall wind up for today.
Okay, sir.
Okay. Now tell me when we shall have our next class and in which mode. Scheduled class is on Wednesday, na? Second up.
Yes, sir.
And so far as I have come to know, Faculty of Engineering and Technology have decided to go for physical mode of class, and from 7th onwards all classes will be in physical mode. So what do you say? I have no objection. Whatever you will say, I shall follow that. I mean, I have no preference to be more specific. Whichever is convenient for you, you tell me that. If you are unable to take decision right at this moment, you take your time and inform me by tomorrow. Will that be okay with you?
Yes, sir. That would be better.
That will be better. So inform me positively by tomorrow. Aniket, are you here? Ahon, are you here? Not Aniket. Ahon, are you here?
স্যার অহন নেই।
নেই। তাহলে তোমাদের সেকেন্ড সিয়ারটা কে?
স্যার
Yes,
সায়ন।
sir.
আয়ন।
Sir,
হ্যাঁ?
হ্যাঁ স্যার বলুন।
তাহলে তুমি তোমার নাম্বারটা আমাকে বলো।
6296
দাঁড়াও 1 মিনিট। তোমার সায়ন কি?
সায়ন কুমার নাগ।
সায়ন হ্যাঁ বলো
6296
6296
226
226
064.
064. Okay, I save it for you. Okay, so কালকের মধ্যে আমায় জানিয়ে দিও, আর না হলে মানে হোয়াটসঅ্যাপ করে দিলেও হবে,
ওকে স্যার।
নো প্রবলেম, কিন্তু আমাকে জানিও অবশ্যই।
ওকে স্যার।
নাও let us call your roll numbers. Roll number 1, roll number 2, এ ছেড়ে দিয়েছে নাকি বলো তো? roll number 5, 6,
Yes, sir. Present, sir.
okay, 7,
Yes, sir.
8, 9,
Present, sir.
10, 11,
প্রেজেন্ট স্যার।
12, 13, 14, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, স্নেহাশিস ব্যানার্জি, সুব্রত দালাল,
Yes, sir.
ফারুক আলী, (31),
Yes, sir.
33, 34,
Present, sir.
37, 38, 39, 40, 41, 42, 43, 44, 44, 47, 48, 49,
Yes, sir.
50,
ইয়েস স্যার।
51,
Present, sir.
52, 54,
Present, sir.
55,
Yes, sir.
56, 57, 58,
Present, sir.
1004,
Present, sir.
1005, 1006,
Present, sir.
59,
Present, sir.
60,
Present, sir.
61, 62, 63,
Yes, sir.
64, 65, 66, 67, 68,
Present, sir.
69, 70, 73, 74, 76, 77, 78, 79, 80,
Yes, sir.
81,
Yes, sir.
83, 84,
Present, sir.
85, 86, 87, 1007,
Present, sir.
1008,
Yes, sir.
1009.
Yes, sir.
ওকে,
স্যার বলছি কোন নম্বরে আপনাকে ওই মেসেজটা দেবো?
হোয়াটসঅ্যাপ আছে আমার, লিখে নাও।
হ্যাঁ স্যার বলুন।
98300
হ্যাঁ স্যার।
21794।
9830021794।
হ্যাঁ,
ঠিক আছে স্যার।
ঠিক আছে। বেশ, তাহলে লেট আস ডিসপার্স।